Okay, yeah, thanks everyone. Thanks to the organisers as well for the invitation to come and talk to you today about the Gravitational-waveOptical Transient Observer. Now, you're going to get a little bit of deja vu in this talk because a lot of it overlaps with what Heloise was doing, even down to a couple of the plots. But I think Heloise sort of concentrated on other stuff to what I concentrate on for GOTO, so that's nice, quite complementary. So first of all, what is GOTO? GOTO is a collaboration mainly of UK institutes, but with a smattering, particularly in Australia and in Europe. And it's a series of optical telescopes which is aiming to survey the night sky and follow up triggers from different alert streams, different messages, and multi-wavelength. It's PI by Paris-Saclay in Warwick. Science motivation is just in this one slide. We've heard a little bit about various aspects of these, so I won't dwell on the point really here. I guess Eloise mentioned how Atlas is designed for solar system objects. GOTO from the ground up was built for multi-wavelength and multi-messenger science. So its primary aim is to react to triggers from external alert streams, particularly the ones I've highlighted with the photons, sort of dashed borders, because those are the ones where we expect some sort of optical emission to come from these. We're not as interested in things like black hole emergence, for example. So we're wanting to survey the dynamic of multi-messenger universe. In terms of design specification, this goes back just over a decade now when the initial sort of thoughts about building a dedicated facility, and this is sort of mock-up from the artist's impressions of how this might look. It builds on a bit of a heritage we have at Warwick, which is sticking lots of telescopes on a small number of mounts. It allows you to produce quite cost-effective but scalable facilities. And the idea being that a lot of these telescopes are somewhat off the shelf, so you can replace them, you can continually update, and you can have a staged deployment, which allows you to prototype various things before you sort of commit to one big telescope. So of course, the contrast with something like the Vera Rubin Observatory is quite stark here. So indeed, we had this staged development which began sort of in 2017, and there's paper stakes 2022. You can read about the prototype system. So we stuck 4 of these unit telescopes on a mount in La Palma. Each one of these telescopes about 40 centimeters aperture, got several square degree field of view. So again, you've got Andromeda sitting here. That's the field of view of just one telescope. And a lot of this time was spent really to learn about the system, learn about the OTA design, learn a lot of issues about which telescope manufacturers and optics manufacturers you should avoid. And we tweaked that and we used it to sort of iterate on the design of the optical telescopes, iterate on the design of the mount, in order to promote for full development of what we always envisaged would be a multi-site, multi-telescope facility. So the prototype system was retired in 2020, and we entered a period of development to get to the full system. Now, 2020 was a bad year for international travel, unfortunately. We had the pandemic, and things on La Palma particularly got a lot worse because there was also, once things opened back up, the volcano decided to go off, so things were getting quite biblical on La Palma. We didn't quite get the locusts, but this really sort of hampered our development timeline. This was all meant to be compressed in sort of 18 months. It was stretched out over 2 or 3 years, unfortunately. But during this time, as I say, we learned a lot of lessons about the exact design. Okay. And we entered in 2023 what we would call sort of the full design and what we'd always envisaged GOTO to look like. So GOTO, as it currently sits, is 4 mounts, now each with 8 telescopes on each one of those mounts, and they're situated in 2 sites in La Palma and in Silent Springs in Australia. The wide optical filter, I realised I didn't put in a slide on the actual filters, but it's basically what Heloise was showing for the wide filter on the right-hand side of her slide, 400 to 700 nanometers, very much in the optical. We're trying to just get as many photons as we can because we're relatively small aperture telescopes. And the idea is that we'd always run this in an automated fashion. There's no human in the loop making decisions about what to follow up, what to observe next. It's fully autonomous scheduling and with a real-time pipeline. This is where the deja vu comes in, a very similar plot that Heloise showed, and just showing the location and sky coverage of GOTO quite nicely. These are almost exactly antipodal sites, and it means that they very rarely actually can observe at the same time. So we can get away with the computing infrastructure to just handle one node, because when it's daytime at one, it's nighttime at the other. little bit outdated because Atlas doesn't say it's got 5 nodes, it says it's got 4 on here. This is from a few years ago, but again, just a field of view comparison. This is one site effectively of GOTO. We have about 80 square degrees, a little bit more now, actually about 90 square degrees. And what that boils down to is a couple of day cadence survey on average. But as I mentioned, GOTO is very much reacting to triggers from other wavelength and other messenger facilities. And so for large areas of the sky, we typically have sort of hours cadence, on maybe, depending on what's going on in the night sky, hundreds to thousands of square degrees. Control and scheduling is done by Martin Dyer at the University of Sheffield, and there's a series of SPIE papers here describing GTEx, which is the automated system for actually controlling the telescope, making the decisions on scheduling and actually enacting the observations. And you can see a couple of examples here on the right. This is for a gravitational wave detection, and this is for a Fermi GRB alert. This is handled all automatically. Alerts go out to our Slack space, and we integrate sort of a follow-up strategy depending on the nature of the alert. We have a tile-in system. It sort of optimizes where we should look on sky with GOTO and when, in order to maximize our chances of recovery of the proposed counterpart. All things like environmental constraints and everything are handled automatically, so if it starts raining, the domes usually close. In terms of the real-time side of things, so once we actually take the data, we've heard a lot about difference image analysis. We're doing exactly the same here. A lot of things Heloise was talking about, I won't touch on, but similarly, we have a real bogus model, which is sort of telling us, is this thing real or is it bogus? On the left-hand side here, just concentrate on the black lines, really. And this is the delay time from GOTO shutter close until when we fully process the image and send out our candidate alert to our internal systems. So this hasn't really been optimized at all, but we're already at sort of 5-6 minutes from shutter close. So actually, the collaboration members having eyeballs on objects. That could very much go to the left with more intelligent software. So on the right-hand side, we've got heat maps here of image depth as a function of moon illumination, which is the primary thing affecting these. We operate in 2 main modes. This is just the regular sky survey on the left. We're hitting sort of 20th magnitude, and we go slightly deeper because we're looking at a targeted subregion of the sky, so there's on average a slightly deeper. This is a little bit of a pessimistic view of what we currently have, because a few weeks ago, someone went out and cleaned one of our secondary mirrors, and we got a magnitude improvement in the 0 point immediately. So there's a couple of people out there now cleaning off, so these should go down by magnitude also in the very near future. We have our own internal, what we call Marshall system, very familiar in sort of time domain, particularly optical surveys. This is a GOTO collaboration tool where we can analyze the site kind of alerts that come in, make decisions based on contextual information, which you can't read on here because it's too small. And we have a bunch of buttons which allow us to also trigger external facilities. So we want to get some multicolor information. We want to take a spectrum, for example. We can do that in the Marshall. Here's just the cumulative TNS report. So the sort of community notices, essentially, of electromagnetic transients that we found. And we're remarkably consistent, actually, over the last couple of years since we've been in full operations. Within the Marshall, we also look at doing cross-matching independently of what the telescope thinks it's doing. So the telescope might not have responded to a historical alert, which comes out with some delay, for example. So the Marshall is completely agnostic to what the telescope's doing. It listens also to all these alert streams, and it does its own cross-matching of sources, which are these tiny little dots on top of the sky maps here. And is a very densely populated one here because we hammered this. This was a relatively confident neutron star black hole system. And there's a whole bunch of calculations done within the Marshall, which give us some broad overview of how that follow-up went, essentially. And the idea is soon to tie this in with a recovery code called Jerry by my previous postdoc, David O'Neill, with the main aim of sort of quantifying actually what, particularly on non-detections mean. So not just telling people how much of the sky map you cover, for example, but actually putting quantities on whether you should have detected the transient that you're searching for in those data. Just a couple of highlights on the science then that we're doing with GOTO. I mentioned that we follow up things like Fermi GRBs. These are typically hundreds of square degrees that need to be searching. Sounds like a bit of a challenge, and they look actually quite small in here because of the scale, but these are hundreds of square degrees. Each one of these is a GOTO point in, and we're getting really good now at finding these GRB afterglows. independent of any arc-second localization. So we've got a sample paper here by Amit Kumar, just been published, and focusing on one example here on the right-hand side. This was a short camera burst. This is work by Dimple recently. It's potentially, if you think it's a merger-driven event, the most distant merger-driven event that we know of. And you go and follow up the GOTO location with JWST, and you find a nice little host galaxy at the position of that short camera burst. Every so often, serendipitously, because of this dense high cadence coverage I was mentioning, you get very lucky. And so ZTF with these 2 green points announced a fast fading transient, and we go back and go to data and we see we actually had a 1.5 hour non-detection window. Gives you a very small window to search for high energy emission, and there was no high energy emission from any of the surveys. So what we think of this is an orphan afterglow. We see the afterglow and we see the supernova rising, but we didn't get any high energy emission associated with this. And you wait for the supernova to rise, and you can get a nice JWST spectrum of a supernova at redshift 1, which is quite incredible to think about only a few years ago. One of my pet projects that I've been leading within GOTO is this survey called GOTO Fast. And the idea here is to exploit other robotic telescopes and PhD students and postdocs on the island of La Palma to actually follow up these candidates that we're detecting almost in real time. So we have things like the robotic Liverpool telescope. We can schedule that in software. These other 2 telescopes, they're not, and the INT requires a whole bunch of people to sit at them. But the idea is you sit at those telescopes, and in real time, as I mentioned, sort of 10 minutes after the GOTO shutter has closed, we'll have candidates coming into the Marshall. They can make a decision on whether it's worth going to point that telescope immediately and taking a spectrum potentially within minutes of discovery. It's exactly what we did early in 2024. We were taking a spectrum less than half an hour after GOTO made its first detection of this supernova. We're still observing it 20 months later. It's been observed with X-Shooter. There's JWST programming for this one. It's a very weird one. Thankfully, it wasn't just a run of the milk since we got onto it so early. This is a massive star which has got a very complex circumstellar medium around it, and you see this sort of forest of ionization lines just up and down here, lived remarkably long compared to what we see in normal massive star eruptions. Skim over this one very quickly. This was one done completely by the software. We woke up in the morning to the spectrum, and this is one of the, I think it is the earliest classification spectrum for this peculiar type of supernova, which I won't go into detail at the time. What I did want to talk about is a little bit of citizen science. So we've got 2 people in the collaboration, Lisa Kelsey and Tom Kilstein, doing really great work pushing this kilonova seekers. The actual finding of kilonova has not been not happened, but our volunteers are very enthusiastic. They're helping us search through all of our candidates. And yeah, we've got thousands of volunteers making millions of classifications for us, looking at the difference image stamps, basically. So it's a very successful project. We're doing a lot of outreach as well, using some of the tools here. It was recently awarded a public engagement award from UKRI. So we're going to use that money to make an educational version of this website, which is appropriate for school children to engage in some sort of research project. A highlight, I think, a sort of shining light from this citizen science. This is our science reference and difference image. There's a remarkably bright object came in, and our volunteers spotted this almost immediately, faster than us actually in this case. And they notified us that this was going on. We enacted a big, long follow-up campaign using a whole suite of observatories, and published this paper here, led by Tom Kilstein. This was a very weird dwarf nova, and quite nicely, a lot of the volunteers, which helped us with some of the data acquisition, are actually on this paper as well. So I think that's a real sort of key point that we've had from this project. I'll just wrap up talking about post-04. So the gravitational wave detectors will turn off in around a month's time or so. So what can we do with GOTO when there's no GW going on? What we want to do really is a couple of custom sky surveys. So the one that I'm interested in is taking the sort of middle 30 degrees in terms of the equatorial strip, which both of our sites can see from La Palma in the north and Silent Springs in the south. And then you do something like a 0.3 night cadence. This is almost continually visible from both of our sites. We can start finding these transients regularly within hours of explosion. Other people in this collaboration want to look at the galactic plane and just sit on the same patch of sky for a few hours, search for very rapid variability. In terms of access to the products, I think I'm really pushing in GOTO to get this opened up post-04. We do have a force photometry API, which has been available to a few testers. We're hoping that will get pushed out. Unlike Eloise, I did pick the nicest light curve here that I could find. And we want to have a Kafka producer, which is pushing out some of these alerts to things like the brokers, for example. And yes, that was my final slide. Thank you.